Okay, so the last class I tell you if the your point located at the different fluid will have the different density, right? And then you cannot have the equal piezometric pressure or piezometric head. Okay, but sometimes we will meet the problem is here. How about the interface? The interface between the two fluids and the upper and the bottom fluid are different density. But in that case, we call that the along the interface still satisfy the pressure equal. Along the interface still satisfy the pressure equal. Okay, so this is a condition only for the interface. Okay, between two different fluids. Okay, so the table summarizes all different formulas, but the same ideas for the hydrostatic equations. So you can use the head form, and we call that the 压力头高层头. Okay, and the sum of the pressure head and the elevation head, we call that the piezometric head, 测压头. Okay, and then another formula we use the differential formulas. That indicates the pressure difference is proportional to the fluid gamma and the deflection high, the fluid deflection high. And the final one, we directly use the piezometric pressure form. So we don't divide the gamma. So the pressure plus the gamma Z is the constant. It's the constant. Okay? If the density is a constant. So the bottom just highlights some important assumptions if you would like to apply the hydrostatic equations, and the summarize on the right hand side. So you can check it by yourself. So we move to the first exercise. So the exercise is quite simple. You just put the water. Just put the water on the tank, and the height is the 35 ft. And the question is, how about the pressures located at the P2? How about the pressures located at the P2? Okay, so you try to consider how condition you have. Right now, the problem we locate at the same fluid, so it satisfies the piezometric pressure are constant. Okay, so we can follow the hydrostatic equation. We know that the P1 is here, P1 plus gamma Z1, okay, should be equal to P2 plus gamma Z2, right? Because they are located at the same fluid, water. And then, because we consider the gauge pressures, so the P1 in here, is exposed on the air. So the gauge pressures at the location 1 is equal to 0. Okay, so we don't have the gauge pressure at the location 1 because the location 1 located at the environment. Okay, so you reorganize your equations showing here. The answer we need to tell. We need to find the solution for the P2, and the P2 is equal to the gamma multiply the Z1 minus the Z2. And we actually know the gamma in here. This is room conditions, and we can check from the table. This is the gamma waters, but for the English unit, okay? So the gamma water is equal to the 662.4, and the unit is the bomb force divided the Ft cubic. And the delta D changes is D1 minus Z2. We already know the number showing here is 35 Ft. Okay, so you can compute the answers for these questions. Okay, so I check the number in here. It's equal to the 2184, and because this is a bomb force divided the Ft square, so we can say that is PSF, and this is the gauge pressure. This is gauge pressure. And we know actually the 1 ATM is equal to the 2116 PSF. Okay, so the two numbers showing here are quite similar. So that's the sentence I summarize on the buttons. If you increase the 10-meter depth of the waters, you will have additional 1 ATM pressure. So it's very important information for the water diver when they are in the divers. They need to check from their gauge pressures, so you actually know how depth of the water right now. Okay, and then we know that the 10 meters is around because we know that the 1 Ft is equal to 0.3048 meter. So you can convert the 10 meter by this number is equal to the around the 32.8 Ft. Okay, so the 10 meter over the Ft number in here are quite important for the water diver, because around this number you will have the increase 1 ATM pressures when you are play with the water diver. Okay, so the next questions are different because the same ideas, but the top I put the oil on the top. Okay, I put the oil on the top, and the bottom is the water, and with the different liquid depths. So as I emphasize, only locate at the same fluid we can satisfy the hydrostatic equations. So the first equation I use in here, the P1 plus gamma Z1 will equal to the P2 plus gamma Z2, right? And again, the P1 is posed on the air, so we don't have the gauge pressure. So we can directly compute the P2. And the P2 the same, the gamma multiply the Z1 minus the Z2. And the gamma here is oil. The gamma here, we use the oil. And we don't know oil specific weight. But the questions provide the informations. The SG numbers of the oil is 0.8. SG number of the oil is 0.8. So we know that the gamma in here for the oil is the gamma water multiply the 0.8, right? Because this is for the oil SG numbers, and the Z delta D difference is 0.9 meters. Okay, so the table already tell you the gamma water is the 9810. So use your calculator, you can compute the answer for the P2 pressure. So the P2 pressure is around the it's around the 706.3.2. So the unit in here is the par, right? Because this is a SI unit. This is a SI unit. But the question is, what is the gauge pressure at the bottom? Okay, so the question we would like to answer is for the P3, the P3 in here. Okay, and because the P2, we can make the balance between the P2 and the P3. Again, because they are located the same liquid. So P2 plus gamma Z2 is equal to P3 plus gamma Z3. Okay, so P3 is equal to the P2 plus the gamma Z2 minus Z3. Okay, so we just put the P2 inside. The number is 706.3.2 par, and the plus the gamma. The gamma right now is the water. Okay, so we use the 9.10 Newton per cubic meter. Multiply the depth difference is 2.1 meter in here. Okay, so you can compute by yourself, and then the result is equal to the 2764.2 par. So it's the quite similar answer showing here. They are the same, and this is the pressure is the gauge pressure. Okay, so the idea is because the SG oil is smaller than 1. That means if I replace the oil by the water, the P3 answer will increase. Because I replace the 0.9 meter thickness, the liquid to be the water. And the water, the gamma is larger than the gamma oil. So the same depth, but if I replace the bottom liquid to be the water, and then the pressure will increase. Okay, so that's I highlight for our these conditions, the oil is less than the water, the density less than the water. So will slightly smaller than the pressure corresponding to the water column with the 3 meter depth. Okay, so the idea is quite simple. We only can satisfy apply the hydrostatic equations at the same liquid or at the same fluid. If they are not the same, so you need to make the balance, pressure balance individually. Okay, so like the example showing here. Okay, so as I usually we have do some water divings, and this is a quite simple idea.
水世界好吸引人，民众奔向水中潜水跟鱼儿嬉戏，可是要当心，潜水后48小时内，如果搭乘飞机，可能罹患潜水
这个很
病，
重要，
严重
就是
怕致命。
所以，如果我们在潜到比较深的地方呢，事实上氧气、氮气融化到血液的，如果你上升太快的时候呢，就要像一个汽水把瓶盖打开，那一旦就必须落后，这些空气都跑出来。
每下降海平面10公尺，就会增加1大气压。深潜海底超过30公尺，稍有意外，身体压力骤减，体内空气会变成4倍大气泡。 气栓塞住组织，造成器官功能失调。减压症俗称潜水夫病，潜水后24到48小时内避免到海拔600公尺以上。假设到绿岛潜水返程不能搭飞机，也建议不要走南横回西半部，因为最高海拔可能来到2400公尺。它的致命处在于发生症状可能会被忽略。
潜水呢，然后上升了以后，什么时候你要？
所以你看这个新闻已经是一般的知识。你只要下潜10公尺就会增加1大气压，
头痛。
所以你再下潜10公尺、20公尺就会再增加1个1大气压。所以通常大家可能不知道1大气压的可怕，可是如果你潜水的时候直接飘上来，
及早发现才能给予治疗。
本来在深的地方压力比较大，你很快飘上来，那些气体会跑出来。那我们知道气体如果释放出来的话，我们不是说那些气泡都很可怕吗？所以有些时候我们肺里面的肺泡也会这样就破掉了。那我们肺泡破掉的话，就跟武汉肺炎一样，
留意自身状况，如果有异状，及早就医检查，才不会错过抢救的黄金时间。关新闻地方中心在台北报道。
一般我在秀这个的时候，像每次上课我都会秀以前我自己在练潜水的时候，因为当然那些照片就被检举说老师一直漏点这样子，所以我就这样的课我就不乱秀了。因为我在当兵的时候，我是水下作业大队，所以我们有3个月的潜水训练。然后，如果大家有玩潜水的人知道，你自己在外面学潜水不是开玩笑的。第一个你要有钱，第二个你要有教练带，然后第三个你拿到执照的时候，你要潜水很简单，你一定要吸多少支气瓶，就是你潜了多少次没有关系，是跟你吸了多少个气瓶有关系。所以你要吸超多次的，你要把气瓶用掉会登记嘛。然后最后你要考执照，你一定要吸好几公升的气，来代表你有真的去训练嘛。那会潜水其实有很多好处啊。如果大家去吃热炒店，点一盘凤螺，烤凤螺大颗的大概250嘛，那你会潜水就去捡凤螺自己回来烤就好，就不用钱了。真的，所以我们在国军学的话是不用钱，不过你们现在已经没救了，除非你们签志愿役，因为你们4个月再也没办法去受这种训练。我介绍超多人进去。那你学完就出来嘛，反正你就退伍了。所以我们现在像我身上有 Open Water Diver 可以潜60米的自由证照，可是我不能教别人，但是我可以自己去潜水，就是没有人管得了我这样子。那如果你在外面学的话，光考这个证照就要10万块，就是学习的整个程序要10万块。那你签志愿役也没有什么不好的，志愿役2年以后可以放弃2年以后可以放弃，免费放弃。那1个月的薪水，当3个月以后，1个月的薪水就有3万多，1个月薪水就有3万多，当然跟台积电是不能比的啦。题外话，这个我有录下来，这个很重要，跟学弟好好讲一下。Okay, so but the previous slide we always focus on the liquid, but we know the fluid we still have the gas, right? So the slide just show example, focus on the material is the gas, and how difference. So the significant difference for the gas, the gamma is totally different. As you see, if we consider the gas is the air, it's the air, okay? And we actually know the air density is 1.2, right? And the kilogram per meter cubic. But if you remember, for the water is the 1,000. Okay, for the water is 1,000. So the liquid density and the gas density totally different. That indicates the gamma in here, low G in here is quite smaller. As you remember, the 1 ATM is equal to the 101.3 kilopar, right? But the Pascal in here, uncomparable. That means the gas, the gamma is quite smaller. So usually we will neglect the effect from the gas. That means the gas change contribute to the pressure are quite smaller. Okay, because we know that the delta P is equal to the gamma delta Z, right? If the gamma is quite smaller, no matter the delta Z changes a lot, but the delta P is still small. Okay, so for the gas problem, sometimes we neglect the pressure difference caused by the gas. Okay, we only focus on the liquid. But additional one difference also, for the gas, usually we say that the inhomogeneous fluid, because the density can be changed. The density can be changed. So as you see, the gamma can be equal to rho G, and based on the ideal gas law, the ideal gas law tells us the P is equal to rho RT, right? So we can replace the rho to be the P divided the RT. Okay, so you can replace the rho by these items. And we know that the temperature in here is the function of the elevations. The elevation increase, the temperature decrease. And so there is the minus here, and the alpha is the temperature gradient. The 1 kilometer increase will have the minus 6.5 degree change. Okay, so if we put all of them together, so for this problem, we actually know the gamma is not constant. The gamma is not the constant, and the gamma is a function of the temperature, and the temperature is a function of the elevation change. Okay, so you can try to practice by yourself. You can integrate these equations, and you will have the final result like. So you know that the pressure at the sea level multiply the 1 minus the sea level temperature first the alpha, and the elevation changed here, and we have the power. The power is the ratio between the gravity and the gas constants, and also have the alpha temperature gradients. Okay, so for the gas problem, the pressure change is quite complicated compared to the liquid. Okay, liquid usually we just consider how much difference between the elevations, but for the gas we still need to consider the gas constant values and the temperature at the sea level, and the delta Z difference and the temperature gradient. Okay, so you can try to practice by yourself. Okay, so this is the alpha in here. You see the alpha in here. The x-axis is the temperature, and the y-axis is the altitude. So you see the alpha gradient is the slope of this line. But if you go to the stratosphere, the temperature gradient will change. It will be the increased. Okay, so but sometimes the engineering problem we are focused on here, not in here. Okay, so the gradient you can keep in mind the number in here. Okay, so now the topic we move to how can we know the pressures. So that is a very simple idea. We put the barometers, 水银压力计, okay? And the important thing in here is we need to observe the high, the rising high. And if you take a look, there is a confine, it's a closed tube. It's the closed tube. And then you put the barometer on the air, you will see the rising high. And then you actually know the rising high is equal to the 762 millimeter, right? But how can we compute the numbers of the 762 millimeters? So go back to see the equations in here. The PATN is equal to the gamma Hg, right? How high of the Hg? So gamma Hg multiply the deflection high is the pressure change, right? And then we need to additional plus the PV. PV is the vapor pressure. The vapor pressure located in here. We have a vapor pressure, but the vapor pressure is the gas. is the gas, and the vapor in here is mercury gas. Okay, so if you check from the table for the mercury, the vapor pressure is quite smaller. The number shown here, the vapor pressure is quite smaller. It's 10⁻⁶ power atm. Okay, so usually we neglect the items for the vapor pressures. And then finally, we only have a P atm, and we have the gamma Hg, and we can compute the theoretical diffraction height for the Hg material. Okay, and another problem in here, as I mentioned, if we put the liquid into the tube, you need to consider surface tension effect. You need to consider the surface tension effect. But when we design the tube, we use very large diameters. The diameter is larger than 1 centimeter. And then we can neglect the capillary phenomena. If you go back to see the equation for the surface tension, as I teach in the surface tension chapters, so you know that the rising height is equal to the 4 times surface tension, and divided the gamma d, right? So if I design the d is increased, that means the diffraction height will decrease. So if I use the tube with the larger diameters, I can neglect the effect of the surface tension. Okay, so when we design the barometer, we will use the larger diameter of the tube. We will use the larger diameter of the tube. And the second, this is in our life, usually we use for the bicycle or the basketball, okay? And then you see, the idea is the inside we have the spring. And if we sensitive to the pressure changes, the spring will have the external force. And the spring will adjust the pin line to change the pressures. But for this device, it's not convenient because it only can measure very low pressure. If the pressure is relatively high, you cannot use the device to measure the pressure. So I'm not suggest for this, okay? And then if you put the tube inside the flow, and then you have the flow, and you can have the diffraction height. And for this device, usually we call that is the piezometer, 静压管, okay? And we know that the height and the flow, and we know that the pressure difference between the 0.1 and the 0.2. And as I mentioned, usually the 0.1 is high and the 0.2 is low. And then the difference, delta P, is related to the H difference. Okay, so usually we will say that the delta P is equal to gamma H, okay? But this device is not very useful because you need to bring the device to anywhere you would like to measure the pressure. And for some questions, if your flow velocity is quite higher, you will have the large H rising height. If your height of the tube is not large enough, you cannot measure the flow velocity. So not convenient, okay? So another solution is we use the U-shaped tube, and then we call that the U-tube manometer, okay? So, and for these questions, we think the inside is the gas. And again, because they are the same, they in this color we focus on the gas, and there is some different fluid material. We call that is manometer liquid. We call that is a manometer liquid. Okay, gamma m. So we can make the balance. We can start from the here, the point 1, the P1. Okay, and then because the P1 always equal to 0, right? Exposed on the air, and we plus the gamma n is the manometer liquid, and the delta H in here. So P1 plus gamma n delta H is equal to P2, right? Is equal to the P2, and the P3, so it's equal to the P2. And the P3 in here, they are the same elevation. So the P3 is equal to P2. Okay? And then how about the P4? Because this is the high is the rising. The high is the rising. The high is the rising. That means the pressure is decreased. So the P3 minus the gamma, right now the gamma is the gas gamma, because the material in here is the gamma, is the gas. The gamma gas minus the gamma gas L will equal to P4. Okay? So our purpose is how can we measure the P4 based on the U-shape manometer. Okay, so you can make all of the balance together. That means because we know the P2 is equal to P3. So the P3 is equal to P1 plus gamma m delta H. And P3 minus gamma gas L is equal to the P4. So finally, we know that the P4 is equal to P1 plus gamma n delta H minus gamma gas L. Okay? And then you see the P1 we can cancel out because the P1 is on the environment. Okay? So that is equal to 0. And we can link that to the gas effect because the gamma gas usually is smaller than the mercury gamma. Okay, so we also ignite the gamma gas. So the P4 pressure finally is about the gamma m multiplied the delta H. So this device can decrease the deflection height in here because I use the U shape. So the deflection height only the delta H, smaller H. So the right hand side, the U tube shape is better than the left hand side. Okay, so this is the idea. So this is the two questions. As you see, right now I replace the gas by the water. So the inside the material is the water. Inside material is the water. Okay? So again, we know that we have the P1, P2, P3, and the P4. So you based on the idea, if the elevation, the H increase, that means the pressure decrease. If the H decrease and the pressure increase. Okay, so I start from P1 because it's a downward, right? So the pressure increase. So I plus the gamma mercury delta H, and I go to the left hand side. They are located at the same elevation. So P3 is equal to P2. And then I rising the L length. The length increase, I indicate the pressure decrease. So I use the minus, but then right now the liquid is the water. So here I use the gamma water and multiply the length, and then finally equal to P4, right? So going down, increase the pressure, and the left hand side going up, so decrease the pressure, and then we go back to the P4, okay? And in that case, we know that the P1 is 0, so finally we cannot neglect the effect from the water. In previous slide, we neglect the gas, right? Because the gamma gas is quite smaller compared to the gamma M. But the gamma W, we can't neglect in that conditions. So the P4 in here is equal to gamma M delta H minus the gamma W L. And the gamma M showing here, we have the gamma M in mercury, and the 133,000 newtons per meter cubic multiply the delta H. Delta H in here, 0.6 meters minus the gamma W is 9810 Newton meter cubic, and the L in here is the 1.8 meter. So you can compute the gauge pressure located at the P4, located at the fourth station. 133,000 multiply 0.6 minus 9810 multiply 1.8. So the answer is the 62142 par. Okay, so it's quite close to the answer showing here. And please remember, we calculate the pressure relative to environment. So the pressure unit is gauge pressure. We usually have the problem and require you answer the pressure. We compute the pressure is the gauge pressure, like here. So inside the pipe, because we know that the 1 atm is equal to 101.3 kilopar, and this compared to pressures, the pipe inside the fluid, the pressure is half of the 1 atm. Okay, half of the 1 atm, around the half of the 1 atm. Okay, so this is our exercise. Okay, I think the time is almost close to the 12, so maybe we just stop here. Okay, so今天的重点就是大家要去善用静压方程式。那算了几个 exercise， 大家就会知道很简单嘛。只要是抬升，高层抬升就是压力下降；只要是下降，压力就会增加。所以你什么时候要减，什么时候要加，你要特别的小心。第二个是 Hydrostatic Equation 的 balance 只能用在同一个 density 的密度，同一个密度。那你不同密度你也可以用 balance， 但是你要记得要转换。所以 gamma 不要带错，然后想一下这个 gamma 合不合理。OK， 好，那大家准备一下